In SDM, there are two main categories, multi-core and multi-mode. For multi-core, the fibers themselves are harder to make, but everything else about the system is easier. It's single-moded, you're moving Gaussians from point A to point B, and even though the channels are very closely packed, they remain spatially separated the whole way through the system. So it should be fairly compatible with existing switching technologies. I'm going to be talking about multi-mode. In contrast to multi-core, the fiber is easier to manufacture, but every other aspect of the system is more complicated. The channels occupy almost identical space, and teasing them all apart is what makes things difficult. I'm going to be focusing on LCOS technology here. I'm a big fan of spatial light modulators. I don't think anything can really compete with them, at least in terms of their flexibility. You've got an optical phase element you can program arbitrarily with like HD resolution. The technology behind them is driven by the very large consumer displays market that exists entirely independent of what we want to use them for in telecoms. CMOS has a similar dynamic. It's driven by a massive outside consumer market, which makes it cheap and powerful and allows us to do things like DSP without having to develop the technology from the ground up ourselves. Typically, in an MDM system, full N-by-N MIMO processing is performed, and as a consequence, all modes at a single wavelength must be routed together, as you'll need information about all of them to get your channels back. So in that scenario, switching is performed only on a wavelength basis, like it is in current systems, but with a more complicated beam profile. In a standard LCOS WSS, you use a grating to disperse the light across the array of pixels, and you program different blazed gratings onto the surface of that device such that different bands of wavelengths are reflected at different angles towards different output fibers. Here we have the phase surface of the LCOS, the spatial light modulator. It's programmed to route a particular band of wavelengths to a particular output fiber as per the blazed grating in the middle there. As you tune the wavelength, you scan the Gaussian across, and you get a response like that on the right. How much spectral passband a channel sees depends on what space it takes up on the LCOS. Now for the multimode case, if you're just switching all the modes at the same wavelengths at the same place, then you can still use that blazed grating, but because each mode has a different beam width, a different effective area, like each mode is going to see a slightly different passband. The band of pixels was fine for the fundamental, but you can see that it's too small for the higher order modes. So how closely you can pack your channels in wavelengths will depend on the width of your highest order mode. Okay, so you've got two dimensions, mode and wavelength. Maybe you shouldn't make them share a single axis on the LCOS. Ideally, it'd be nice to be able to assign one axis to the spectrum and the other axis to the modes. Now you can program independent patterns for the different modes, which could help you keep the passbands more consistent, but it will also allow you to independently route modes at the same wavelength. Say if you're operating in the weak coupling regime, maybe with something like a vortex fiber. The way I've been splitting up the signal on a per mode basis is using this system. Light from the multimode fiber comes in here, passes through some polarization diversity optics, reflects off, or in this diagram passes through the SLM, before being recombined using another set of optics and focused onto an output fiber array. Here's what that system looks like in practice. Light comes in, splits into two polarizations, reflects off the SLM before being recombined and focused onto the output fiber array. The principle of operation is that the phase masks programmed onto the SLM are designed to form the correlation peaks for each of the modes at different spatial positions, which corresponds with the positions of the different output fibers. The SLM is obviously programmable, so using this architecture you can route any mode or superposition of modes to any output fiber. You can broadcast to multiple output fibers, you can adjust the attenuation of the modes as they pass through, you can decompose the beam to find the amplitude, phase, and polarization of the mode, you can tap off power on a modal basis. You can do a lot of things with this device. It's a pretty neat contraption, if I do say so myself. But people always ask, what's the loss? And it's at that moment that I become filled with a deep sense of sadness. You could say that my mood incurs a 3 dB power penalty which no amount of DSP can compensate for. Now, early versions of this system had high insertion loss due to the fact that they were made using visible wavelength SLM. Currently, if you plug in a single mode fiber here and a multi-mode fiber there and program a blaze grading with aberration correction onto the surface of the SLM, there's about 3.5 dB loss, which is basically just the reflectivity of the SLM itself. And you could use more reflective SLMs and decrease that further. But that's not the loss mechanism you have to be worried about. The important loss mechanism is how the loss scales as you increase the number of modal channels. You can see that loss at play in this slide, because that phase mask programmed onto the face of the SLM is performing the correlation between the beam and all the channels. So it's not just the autocorrelation. So you can see that the other output fiber positions, there's light there. That's the cross-correlation between the mode you've illuminated the mask with and the mode assigned to that output fiber. Now that distribution doesn't couple into a single mode fiber, so you're not paying an isolation penalty, but you're paying a loss because obviously there's light that's being discarded by the system. In effect, the mask is performing a beam splitter-like operation, sort of like a beam splitter where the splitting ratio is not constant across the entire clear aperture. It is better than a bulk optics beam splitter because it knows about and can exploit the fact that the different modes occupy slightly different space. So for example, if you have one channel on the fundamental mode and one on a higher order OAM of increasing order, you can see how eventually the two become so different they occupy entirely different parts of space with virtually no overlap, and the SLM can perform an operation which is like basically a mirror with a hole drilled through it. One passes through and the other reflects off. But now you're in a regime which is actually more like a multi-core / multi-clad fiber, which obviously negates some of the point of going to multi-mode over multi-core in the first place. So you can use this system to do several channels in normal fiber, but you're never going to be able to do like 100 channels using that scheme. So I think the trade-offs between loss, optical complexity, and DSP complexity that we see on the MUX-DMUX side is also evident in the switching. You can take the full MIMO approach, makes the switching easier because you're only switching on the basis of one variable, wavelength, which is already what we do now. But how scalable is that in the electrical regime? If you are in the weak coupling, low MIMO regime, where modes or groups of modes are processed independently, then the scaling issue is in the optics. There's currently no way to losslessly demux and process the beam on a per mode basis.